Thank you very much, Sarah, for the introduction. I'm very happy to be here to talk about entanglement entropy. This is my first time here, and I really like the place. Thank you. And okay, let me get started. This is work based on paper soon to be submitted, and also a bunch of other papers that appeared earlier this year. I'm going to talk about holographic entanglement entropy and how to go beyond Einstein gravity. So let me first introduce entanglement entropy. It's basically a measurement of quantum correlation between two subsystems. So in general, when we have a quantum system, we can divide the Hilbert space into two subsystems, and we can define a reduced density matrix by tracing out its complement. So let me focus on A, a spatial region A. Then the entanglement entropy for A is simply the von Neumann entropy for the reduced density matrix that we can get from tracing out A's bar. This is a quantity that has been found a lot of uses in a lot of places. In particular, let me just introduce that in quantum information, it has to do with robust error correction and communication. And also, in quantum field theory, it gives us a very nice and natural C function, or sometimes called the F function or A function, depends on what dimension we're in, which is monotonic under the RG flow. This is because it naturally satisfies an inequality called the sum-strong selectivity, and this has been worked on in certain dimensions. Entanglement entropy is a very nice non-local order parameter for novel phases in condensed matter systems. And I think one of the most interesting uses of entanglement entropy relates to how we understand quantum gravity, because our current understanding is that it probably involves information processing in some essential way. There is a deep connection, in particular, between entanglement and space-time. This particular version of this has been dubbed ER equals EPR, which says entangled pair, EPR pair, can in some sense be thought of as geometrized as a wormhole connecting the pair. And this also found uses in how to understand black hole and the information paradox. In this talk, I'll mostly focus on the holographic entanglement entropy because it's most solidly understood. By that, what I mean is simply an entanglement entropy that is defined on a non-gravitational theory, but we can use the holographic dual to calculate the entanglement entropy. And I should mention that it is a very nice way to probe the connection between entanglement and space-time, because it tells us in a sort of way how space-time emerges from a non-gravitational system. The area, as I will talk in just 1 second, the entanglement entropy can be geometrized, and therefore it's useful to understand how geometry emerges from a system like that. So I should mention that entanglement entropy is generally a very complicated quantity to calculate in a generic system or for a generic partition of systems into two systems. Computationally, it is generically very hard, numerically involves Monte Carlo, and analytically can only be calculated for a non-holographic theory. It only can be calculated in very, very special theories. Even in free theories, it is not a trivial matter to calculate this. But holographic entanglement entropy has been particularly very simple. So let's review that. It is a remarkably simple formula when we have a quantum field theory with a holographic dual. In this case, let's focus first on Einstein gravity dual for review. This is being given by, the proposal is that it is given by the area of the minimal surface that is anchored at the boundary of A, the region that we want to compute the entanglement entropy. But the minimal surface extends into the bulk, and we calculate its area in Planck units. That gives the entanglement entropy. This was proposed by Rua and Takeonagi in 2006. At the time, it was a conjecture. it was observed that it satisfies a bunch of checks. It satisfies strong subadditivity. Actual proof of strong subadditivity is actually easier than in general in field theories. And it recovers also known results in 1+1 dimensions when the region A is just a single interval. It was first derived for a very special case, a spherical, when A is a spherical surface, a disk or a solid spheres, by Myers and other people in 2011, because they observed that this quantity, the entanglement entropy for spherical surfaces, can be recast into a problem of black hole entropy for a certain kind of hyperbolic black holes. And one can then use ADS-CFT to solve it. And earlier this year, it was proven for 1+1 dimensional CFTs in general, using very different methods, and also by Lukois and Malasena, they proposed a general derivation just for Einstein gravity, which I will review in a second. I should mention that there are also calculations of corrections to this formula. This is a classical formula. It's valid for in a large n limit. So one can imagine doing 1/n calculations, which involves doing a one-loop calculation in the bulk. This has been done by me and a bunch of collaborators, and also by Brockman and Al. And there's also a remarkably simple proposal for how to do this in a theory of higher spin gravity, where they propose that we should simply replace the area by a Wilson line. But let me ask a natural question, which is how should we generalize this to non-Einstein gravity theories, which, for example, involves higher terms in the curvature tensor, the Riemann tensor. What should we replace? Is there a similar thing we can simply calculate and minimize, and what replace that thing, what replace the area in the Rho-Takayanagi formula? And this is analogous to how Wald entropy generalizes the Bekenstein-Hawking entropy for the case of black hole physics. So there's Bekenstein-Hawking entropy simply says we take the horizon area, that's the entropy for the black hole. In a theory with general higher derivative gravity, there's a proposal by Wald in this form where you simply take the derivative of the Lagrangian. Imagine Lagrangian is some contractions of a bunch of Riemann tensors, and you project to this direction, the two directions orthogonal to the horizon. So these ends are just projectors to those two orthogonal directions. This is evaluated on the horizon. The horizon is codimension 2, so it matches. If we want to, the natural proposal is that we might be able to just use this for entanglement entropy. But we actually have two questions for entanglement entropy. What gives the entropy itself, and where we should evaluate it? So for Rho-Takayanagi, it gives the answer to both questions is the area. We should minimize the area and then use that area to evaluate as the entropy. In principle, these two are independent questions, as we will see. And even before Wald, there has been a different formula proposed by Jacobson-Myers for a particular theory of higher derivative gravity called Lovelock gravity. I'll define it later in the talk, but right now it's just enough to note that it's a different formula from the Wald entropy formula, and they differ by terms involving extrinsic curvature only, extrinsic curvature of the horizon. However, these two formulas were both derived when the horizon is a Killing horizon, and therefore the extrinsic curvature necessarily has to vanish. Therefore, they agree. However, if we do an entanglement calculation, the surface that where entanglement entropy calculation is generally does not generally have zero extrinsic curvature. This is already clear if we simply do the Rho-Takayanagi calculation in a rectangular shaped geometry, and one can just explicitly solve everything and work out the extrinsic curvature is non-zero. So therefore, these two proposals, at least if we try to take these two proposals differently, they give different results. And it has been argued that the entanglement entropy cannot really be the Watt entropy by Myers and collaborators, at least in the theory called Gauss-Bonnet, which is just log gravity at 4 derivatives. This is a very particular theory. The reason they argue that it cannot be the Watt entropy is because the Watt entropy gives the wrong universal terms to the entanglement entropy. Those universal terms were predicted by field theoretic means, and Watt entropy just doesn't give them. And they also checked that the Jacobson-Myers entropy seemed to pass this consistency checks. So they conjecture that this is the right thing to calculate in this particular case.
Can I ask a very basic question? Why would you expect the Watt entropy to agree with the entanglement entropy anyway?
No, it's not. We don't expect that, and we'll see that it's not. It's just a simple thing that comes into your mind when you try to ask this question. Because someone has already worked out the formula, you might ask, does the formula hold?
I will recall its formula is assumed that it's very unquiet, so when there are times which range unquiet. So that might be extrinsic curvature.
Yes, there's an ambiguity in because the derivation of Watt entropy doesn't care about extrinsic curvature at all. It's a killing horizon. And we will see, we will be able to decide those extrinsic curvature terms precisely. So at this level, from a black hole point of view, it's an ambiguity. There's been a lot of recent developments in how to generalize this to particular high derivative gravities, like 4 derivative gravities or Gauss-Bonnet, how to show this for Gauss-Bonnet. And we will see that how our general results match with these special cases. So I thought it would be nice to present a formula at the beginning and then to justify it during the talk. So this is the formula. And you don't have to understand everything right now, just that we have 2 terms as we expect. The first term is Watt entropy. Second term, it comes from extrinsic curvature. These K's are extrinsic curvature, which I'll define later. And right now I just mentioned that this term has the interpretation of some kind of anomaly in a certain calculation. But right now I just leave it as that, and I'll come back to that in a moment. So the outline of the talk is I'll first review the derivation of the Rutak-Yanagi formula, because the derivation in the higher derivative case follows, is based on the derivation of the Rutak-Yanagi formula. And so I'll try to present it in the derivation. I try to present the derivation in a slightly detailed way and rephrase it so that we can generalize it easily. And I wanted to make sure that this is something that everybody can understand. And then I'll talk about how to do this formula for general high derivative gravity. And there's actually another question. There are 2 questions as we see. There's a question of what the formula is and where to evaluate it. So I answer that separately. And since the formula is supposed to work for anything, for arbitrary high derivative theories, but it's good to have examples in mind when we discuss general things. So these are the examples that I'll come back during the talk. The part 1 is just review. One of the most useful ways to calculate entanglement entropy is to use the replica trick. The replica trick says we should introduce something that called reigning entropy, which is log of trace to rho to the n. And the entanglement entropy is simply the n goes to 1 limit of that. The reigning entropy itself can be defined for arbitrary n, but it's most nicely calculable most easily calculable at integer n, because at integer n, it's just a bunch of partition function. It's a partition function on what is known as the n-fold cover. So to define that, let me draw a picture. This is a picture for a one plus one dimensional quantum field theory on a plane, and that's selected the region, the interval, the region I want to compute entanglement entropy as a single interval. This is A. And the n-fold cover is simply we take n planes, cut them, introduce a cut on each at the location of A, and glue them consecutively in a cyclic order. So red to red, green to green, and so on. This constructs an n-fold cover. Let's give them a name, call them Mn, corresponds to manifold with n replicas. M1 is just the original manifold we're considering. There's a nice pictorial way of thinking about how to construct the n-fold cover, which is this angular coordinate around the boundary of A, in this case just 2 points. So the rotation around the boundary of A, we just simply extend the range from 2 pi to 2 pi n. So once we go into the red line, we come out of the red line on the second sheet. This constructs the reigning entropy because, by a very simple one-line argument, because when you do the inner path integral on each plane, you simply get a matrix element of rho in the wave functional basis. So you have boundary conditions for all the fields on the upper and lower edge, and they're just the grand cat of the matrix element of rho. And when you glue them in this way, you simply take rho to the n and trace over that again. So that's a very pictorial way of making things. It's useful to know that that this Mn does not really make sense for non-integer n. So we cannot use this formula right now at non-integer n, take the limit n goes to 1. What we have to do in general is to compute this thing at non-integer n using the partition function, and then analytically continue the result. And that's extremely complicated. Unless we can explicitly work these out, there's just no way to analytically continue. The good thing about holographic theory is that it has been argued that the dual side provides a much better analytic continuation. So we consider holographic theory for this n-fold cover. We can construct a bulk solution. Let's just give them a name, call them Bn. Partition function on the n-fold cover is e to the minus s, the unshelled action on the solution. The basic idea is we can calculate this using gauge gravity duality, and analytically continue the results again to non-integer n, and then extract entanglement entropy. This is still very complicated because in general these bulk solutions are very difficult to calculate. It can be worked out in very special cases, for example in 1+1 dimensions. But the crucial observation of Laplace and Marasena is that we don't actually need all these data, all the family of Bn for arbitrary n. We only need it for n close to 1. And then we just, because we can rewrite the reigning entropy in terms of an unshelled action, and then we just need what this is a little bit away from n equals 1. So if we can find a family of bulk configurations which interpolates between integer n in the right way, we can do this analytic. We can calculate this, even if most of the bulk configurations are not practically calculable. So as long as we can expand in n-1, we're in good shape. So that's the basic idea. To really implement this, one is another crucial idea, a crucial assumption really, which is the replica symmetry. So it's a fact that the n-fold cover has a Zn symmetry, which is associated to tau goes to tau plus 2 pi. It's the rotation which sends you from one plane to the next. It's strictly a symmetry. However, it's an assumption that this symmetry extends to the bulk. Now, this is a non-trivial thing to say. It basically says that the field theory has this symmetry on its Lagrangian, and we also assume the symmetry is not spontaneously broken in a bulk. This agrees with particular cases where we can work out the bulk solution, but it's really an assumption. And let's just take that as an assumption at this point. If we have the Zn symmetry in the bulk, we can consider a quotient space. The quotient space, let's also give it a name. Let's call that B hat. It's an orbifold. It's an orbifold because it's regular except at fixed points of the symmetry. And the claim is the fixed points actually form a codimension 2 surface that is anchored, that is precisely also anchored at the boundary of A. So the picture is you take the quotient of this, Zn quotient of this, you get this picture, and the bulk side has a line of fixed points, which I just give a name as Cn because it has a conical defect on it. And it ends on the boundary of the region A. It has a conical defect at the fixed points because the original bulk solution is assumed to be regular. When we solve the bulk equation in motion, no singularity should be inside. If we now take a smooth space and do a Zn orbifold, it's going to introduce a conical defect with an opening angle that is 2 pi over n. So 2 pi is reduced to 2 pi over n. In a coordinate where we parameterize the angle as tau, as in here, and the radial distance to the surface as rho, it's just the flat metric time a warp factor, which creates the necessary conical defect.
This is one way of introducing conical defect. There's another way, like change the warp something to introduce this conical defect.
I think your question relates to my next slide, which is how to analytically continue. Right now, I'm staying at integer n. So right now I'm making this space by strictly taking the original solution and mod it out by Zn. There is another way to construct it, which is useful. So maybe let's, if your question is not answered on the next slide, then ask me. So let me just comment on how does this help us calculate the entanglement entropy. This is because by construction, the action of the original bulk is just n times the action of the orbifold space. And by that, let me draw the orbifold space like this. The reason I want to draw it like this is because the hat, the orbifold space, the action does not include any contribution from the conical defect. This is obvious from the parent space, because in the parent space, the conical defect, the location of the fixed points is a completely smooth space. It doesn't have any singular contribution to the action. And if we want this to be true, then we had better not to include any singular contribution to the action of the orbifold. So in other words, we cut off the tip, and we simply integrate whatever the Einstein-Hilbert action or whatever the action is from the tip basically from some epsilon distance away from the tip to whatever the boundary is.
But why isn't there an epsilon?
Sorry, but I shouldn't use epsilon. Why is it epsilon?
Well,
I use epsilon for yes. Why is there?
Call it what you will, but
Yeah.
if you
eventually take that to 0. So the prescription is you integrate the action from some, let me use maybe delta. Delta distance away from the tip, integrate to the ADS boundary, and then take the limit delta goes to 0. This is what is meant to not include any contribution. So because you might have expected there's a delta function sitting at the tip. You don't include that. That's all I'm saying. Because there is no delta function in the original space. Now it's plausible that we can analytically continue actually this p hat. It is not plausible that we can analytically continue B because we know in certain cases, and in most cases, the topology of B changes as a function of n. It doesn't make sense to, for example, in 1 + 1 dimensions, it's possible that the number of handles in B is a function of n, and it doesn't make sense to talk about geometries with fractional handles. But once you make the orbifold, you can do that. You can analytically continue the orbifold. So let's talk about how to realize that. There are two equivalent ways to talk about how to analytically continue the orbifold. One is what I call the boundary condition method. It's basically a statement that we just solve all the equations of motion and introduce a boundary condition at a conical defect. This boundary condition is such that it precisely has the right deficit conical with the right deficit angle, and this is the epsilon I'll use throughout the talk. Epsilon is 1 minus 1 over n. This is just an unconventional IR boundary condition. And I won't show this, but you can derive this using considering integer n, and impose the Zn symmetry. And that analytically continue to form the metric near the conical defect. So this is straightforward. There is an even more intuitive method, but it's equivalent. It's called cosmic brain method. It's basically the statement that we can replace the conical defect by a dynamical codimension 2 brain. And the prescription for how to find this analytic continued B hat is to simply solve all the equation of motion resulting from the total action. The cosmic brain will backreact on the geometry in general, and you will also create exactly the right conical defect. It can be shown that it's straight, in the sense that if we now take n copies of B hat together, we can glue them back to the original space that we started with. That is a crucial check, because we want whatever our analytic continuation is, we want it to match with what is required from the replica trick when n is an integer. Yes?
But wouldn't the brain then create a delta function source?
So the question is the brain is auxiliary. So the question is yes. If we solve this, it will have a delta function source. But the statement is we use this as an auxiliary tool to find the geometry, the metric for B hat. And once we have that, we throw out the brain, and we do the same calculation, not including the conical defect. So do what I said on the previous slide. This is just the tool to get the right geometry. So there are two questions now. Where is the defect? And what is the contribution associated to it? Let me answer them in detail. The conical defect precisely becomes the minimal surface as n goes to 1. This is very clear in the cosmic brain method, because the brain just becomes a probe. It is a probe. We will settle down at a minimal surface. In the boundary condition method, where we just impose the boundary condition, it's a little bit more complicated to see this, but it's possible. We just simply look at the ZZ component of Einstein equations. It has a potential singularity, that it has a potential divergence as we approach the location of the conical defect, and has a coefficient which is the extrinsic curvature. The stress tensor is expected to be regular as we take this limit. The reason is this. Again, let's go back to integer n. There is nothing singular at the fixed points in those solutions, and the stress tensor is totally regular. So something has to give. And what gives is this coefficient has to be 0. And this is precisely the formula for a minimal surface. And just one more step we need, which is to compute this thing with the statement that there is a conical defect at a minimal surface. We just need a variation of the action, not including any contribution from the tip itself, to linear ordering 1 over n, 1 minus n. But since we are varying away from a solution, because n equals 1 is a solution to all equations in motion, we simply get something, to linear order, we simply get something which is proportional to the equation of motion up to boundary terms. But the equation of motion is satisfied, so this term vanishes. And we are left with boundary terms only. The boundary term is precisely the area. So we will see, this is a very straightforward calculation. We can just do it by brute force, working out the boundary term. There is a nicer way to do the calculation, which makes it more manifest why this is the area, not something else. And I'll talk about that method when we generalize this to beyond Einstein gravity. Here I just mentioned that the same argument is subtle because of a possible something analogous to anomaly. So let me just summarize the derivation. We construct a conical geometry using the method. We locate it as n goes to 1 by looking at either the brane action or the equation of motion. Then we calculate this variation to linear order. Now we can talk about high derivative gravity. And as I mentioned at the beginning of the talk, this is the formula. We consider I'll just mention here that we consider Lagrangian, which is built from polynomials, let's say, of contractions of Riemann tensor and inverse measure. So throughout the talk, I try to use the capital letters as quantities in higher dimensions and lower letters as quantities in codimension 2 surface. So before going to argue a general thing for how to see this derivation, let's look at why is there a term from extrinsic curvature? Why is it what I call a novelty? Let's consider the simplest non-trivial example, which is 4 derivatives, 2 r's contracted in the most obvious way. We know there is a term in this contraction that comes from the zi, zj coordinate. Let me explain that. So we go to the complex coordinates in the direction that are orthogonal to the codimension 2 surface, and use I and j as the coordinate along the surface. So there is this term. As we mentioned a while ago, this is proportional to the extrinsic curvature times epsilon over z. Now we have 2 of these guys, and we can take this combination, and it becomes something which is of order epsilon squared. And it also goes, roughly speaking, as 1 over the distance squared. This appears to be higher order. So we might say, let's throw it out in our calculation, because we only keep things linear in n-1. Linear in n-1 is the same as linear in epsilon. But this actually contributes to variation of the action at linear order, not at quadratic order. This is because there's a logarithmic divergence if we set epsilon to 0. That means it is very sensitive to any powers of rho to the epsilon that may be present in the integrand, and we should just keep all of those. And when we keep that, there is a 1 over epsilon that jumps out of the integral. So in particular, for this example, we have some powers of, here I've made a typo, these r should be rho. So we have rho to the minus 2 epsilon from the determinant of the metric. And we also have 2 powers of the inverse metric in these 2 directions. And that each of these contributes r to the 2 epsilon. So at the end, we get something which is of order epsilon. This is rather analogous to the calculation of dim red in quantum field theory, and also similar to, as we will see, it's also very particularly similar to Weyl. It's only a similar, it's not the same thing, but feels the same. Now I've introduced that this thing is possibly contributing at linear order. It is hard to keep track of these things because a lot of divergence in principle receives contribution everywhere. And it's very hard to separate this out in a localized way. But there is a method to do that. It's called the regularized cone method, or sometimes called regularized squash cone. Squash just means there's no rotational symmetry.
Is this a way introduced by Solo to keep?
Yeah. They did an explicit calculation for derivative gravity.
But
So this-
some ambiguities, right? In their results. Depends on how you deform this, how you squash this.
Let me
Okay.
talk about that in 1 second. I claim that at linear ordering epsilon, this is just like a anomaly calculation in quantum field theory. The coefficient is regulator independent. But if you're not convinced, we can talk about that. So let me first introduce the method. We want to compute something which is the cone with the tip cut off. We can complete the cone by in a smooth way by some regulator. And we simply subtract out what the inside is. So equation is very simple. S outside is S total minus S inside. Very obvious. The claim is if we take the epsilon derivative, S outside is precisely minus S inside. The argument is simple. S total is finite by construction. It's regularized. Has no boundary at this point. And therefore, the epsilon derivative has to be 0 at epsilon equals 0, because epsilon equals 0 is n equals 1, and n equals 1 is a solution. So we translate a problem of calculating the derivative of S outside into a derivative of S inside with a minus sign. This makes it manifest that this is a localized contribution, and it's easy to do. It's very similar to, again, calculation of Weyl anomaly, because we introduce a regulated effective action. In that case, we separate out terms into a renormalized action and a counter term. And the whole thing is invariant. So whatever the renormalized action, whatever the variation of the renormalized action is, must be opposite to the variation of the counter term. We're just using that term. And variation of the counter term in that case is universal, is regulator independent, as is here. This is not a proof, I understand, but I think it works.
This works for the 2U case, right?
I think it works for general case. That's what I'm going to claim. Maybe if you have a question at a future stage, yeah, please ask. So this is let's really do this. We'll just pick the simplest regulator. The regulator is that we replace rho to the minus 2 epsilon by this thickness A parameter, and we keep everything else the same. This is a different regulator than the one used in their paper, but we got the same result. So if we go back to the simplest non-trivial example, just to illustrate how this works, first it gets a linear combination if one of the Riemann tensor gives this component, because this component is really just a regularized delta function. So it gets whatever its coefficient is. This is exactly the Watt formula. So the second thing is you can receive a contribution from this kind of anomaly, or would-be logarithmic divergences. It must come from two R's, each of which contribute Zi, Zj, and do the same thing. And we can just very explicitly calculate the regularized thing. In this case, it's epsilon over 2. We can put everything together and we can even write it in a covariant form. And this reproduces this paper, the result in this paper by Kusayev. But our claim is this works more generally. It works more generally is because in general, there are only these two ways to get an of order epsilon contribution to the variation of the action. One is when one of them is z bar z bar. This because it's a delta function, so we take the derivative and extract the coefficient. And the other contribution is whenever two Riemann tensors gives a log divergence. There is not an ambiguity when you have more terms, because if more terms go like this, they would only contribute to cubic orders or higher, and no a logarithmic divergence would not enhance that contribution to a linear order contribution. Note that the first term is simply the Watt formula, and the second term vanishes a Killing horizon because it's extrinsic curvature. So this is actually very immediately a derivation of the holographic formula, holographic derivation of Watt's formula for black hole entropy in a high derivative gravity. And this works very generally. And now I have to basically tell you what these coefficients are. It's a bit of technical details, but remember we have almost divergent integral, so it's very sensitive to coefficients of epsilon. And we have to count the coefficients very carefully. So if we write out the decomposition of the higher dimensional Riemann tensor into lower dimensional quantities, we just count how many powers of each of the 2A each one of these guys contribute. And I won't repeat the exercise except by defining this should be QA, sorry for the typo. This QA that appears in the denominator here is the number of terms in the second derivative of L, but we don't count this component QZ Z bar IJ, or the intrinsic curvature of the codimension 2 surface. And we count K squared as one term. This is because this term and possibly this term does not come with the right or expected powers of each of the 2A as the other terms do. So I won't repeat the exercise, but one can convince yourself. So the procedure is strictly you expand this quantity. You first take the second derivative. You expand the quantity according to these equations, and you can forget about all these each of the 2A because these, as long as you count this in the resulting expansion, you necessarily get the right power. So one can think about these normally as normally coefficients. And these are some notations which you had the metric with each of the 2A extracted, and little r is intrinsic, and so on.
I'm still trying to process this. So, okay, I'm going to take the second derivative. That
Yeah.
I could imagine doing.
Yes.
And then bracket alpha.
Bracket alpha, yes, sorry. Thank you for the question. Bracket alpha, I expand the second derivative using these formulas. I just expand it out.
Mhm.
And I get a sum of a bunch of terms. Each term is alpha, so alpha runs over those terms. So for each term, I in principle could have a different coefficient because they have different powers of each of the A.
Okay.
And this Q alpha counts the power for the alpha term.
Okay, so then there's a sum on alpha.
There's a sum on alpha.
Okay, cool.
So it's basically expanding. For each term, you plug in a coefficient, and then you redo the sum. It's just a prescription.
Mm-hmm. Just trying to understand it.
And these things might seem artifact, but it turns out in log-log gravity, these coefficients are exactly engineered in the right way to sum into a nice result that is proposed by Jacobson and Myers by the Gauss-Kardashev equations.
If you couple the metric or the tensor to say flux or other terms, would it be generalized in any straightforward way?
If the coupling is of the type Ricci scalar coupled to them,
But if it's
then
Riemann
this is
tensor,
if it's Riemann tensor, I think a similar story would hold. I'm not sure exactly whether the same formula would hold or not. But I imagine this can be easily generalized to that case. So let's take this formula for a test drive. Let's compare with known results. The trivial results is f of r gravity. It's trivial because one can transform it to Einstein gravity plus scalar. And we can use Rutaki and Nagy for that. And this agrees. I won't show the detail. Another test drive is general four derivative gravity. This is the most general form. And this is the result. If you work it out, in this case, just mention this term does not have any Riemann tensor in it now, because everything is gone. So all the Q's are 0. It's very simple.
Lambda 1, lambda 2 are changed under field redefinition.
What do you mean by field redefinition?
The matrix mu nu goes to R mu nu times something.
Are you talking about a lambda here?
Yes, lambda 1, lambda 2.
The transformation is transformation that, what kind of transformation you are doing?
I shift the metric by a term which depends on which tensor.
You're trying to transform this as in f of gravity into a scalar? Or
No, okay, I can remove lambda 1 and lambda 2 by redefine.
Oh yeah, okay, yes, you can do that.
But the dual field theory only have a unique quantum corrections in it. Which one would be the correct one? Which due to the quantum
What do you mean
correction?
by unique quantum correction?
Yeah, because you are calculating holographic entanglement.
Yeah,
You have a unique dual field theory, I suppose.
yes, okay,
Which
that's,
has unique quantum corrections.
you're saying that lambda 1 is not an independent parameter from a field theory point of view?
Yes.
Um,
Lambda 1, lambda 2, they are not physical. That's my point.
That's probably true, and one would probably see that if we, for example, compute something like the universal contribution, these combine. Let's talk about this in detail afterwards.
Okay.
Yeah, here I'm simply taking the gravity side seriously and do a calculation. So I just mentioned that this works out this explicitly agrees with the explicit calculation by this paper. Now we can also do Gauss-Bonnet theory, which is just a certain combination of the three terms that we just discussed. And if we plug in the formula, we get the intrinsic Ricci scalar out of the codimension 2 surface. This is exactly the prediction of Jacobson-Myers. But this has to work because the previous example works. Now we actually go beyond known results. The Jacobson-Myers entropy seems very nice, and one would hope that it works in general. But it's still derived with in the black hole context. So it's still derived with the assumption that the extrinsic curvature is 0. And we don't know whether it really has the exactly right extrinsic curvature terms or not. The statement here is the formula says it does exactly have the right kind of combination of extrinsic curvature terms inside the intrinsic quantity. So, for example, in 6 derivatives, there has been only a partial consistency check in this paper. The general formula, if we use our formula on previous pages, it gives also the right thing. And remember that the Jefferson-Myers formula is simply the Watt formula, but with the projected Riemann tensors replaced by the intrinsic Riemann tensors. So they differ by all the extrinsic curvature terms that comes into the difference between those two. And those terms are very, very complicated in general dimensions. So, but it turns out there's a very nice form. One can just argue generally that if we take arbitrary Lovelock theory in this form, where delta is a generalized delta function, which is completely antisymmetric in the upper row and lower row, then we use the formula on the previous page. We also get we get entanglement entropy, which is a Lovelock Lagrangian at a lower order with the intrinsic curvature. So I won't show this here, but this works. So let me summarize. This is a formula. We use the regularized cone as a method, and we need to carefully keep some kind of anomaly terms because they would correspond to logarithmic divergence. And this agrees with non-exams. But this formula is supposed to work for arbitrary. So I should mention that this formula, right now we only finished one half of the story in the sense that we have shown that the entanglement entropy has to be this thing evaluated at a conical defect as n goes to 1. We haven't really decided what is the conical defect. Where is the conical defect? So that's the next question we ask. Where do we evaluate this function? Question, of course, the question, we're just trying to find where is the conical defect as n goes to 1. Particularly, we try to ask the question, can we minimize some functional, or in the case of a cosmic brane, what is the brane action that creates an appropriate conical defect in the theory of higher derivative gravity to linear ordering epsilon? In particular, it would be nice if the same formula can be minimized to give this action, to give this conical defect. We will see that in particular cases that I have checked, this works out. So f of r gravity is the simplest, also trivial example. We can, since we already know the result, it has to work. It's simplest to see how it works in the cosmic brane method. We simply add on, let's consider r to the p, and we simply add a brane action which corresponds to the derivative of L with respect to r. And we can write it as a delta function. We only want to solve the linear ordering epsilon, the brane. So we want to argue that this is the right action to linear ordering in epsilon. There could be epsilon squared terms which we're not keep track of. So the most singular terms, we're going to solve basically the most singular terms in the equation of motion from this. The most singular terms comes from the second term. The brane action is when one Riemann tensor provides two derivatives acting, which happens to act on the delta function. This is a very singular term, and we have to somehow cancel it by proposing a particular solution for r. And in particular, the term that we're looking at is two derivatives acting on r to the p minus 1. So we require. So it's clear that we can see R needs to produce a delta function in order for this to cancel. And for that to happen, A has to solve to what is required to exactly produce the right conical defect. So this is a very simple case where you can just work it out and see that the equation of motion guarantees a conical defect. For a general full derivative case, one can also show this. Use the cosmic brane method. So the details are complicated. Instead of going through the details, I'll just mention how we can see the extrinsic curvature terms in this approach. we see them because now if we take, let's say we take the third lambda 3 term, if we look at the equation of motion, it possibly has a component where it has two z derivatives acting on a Riemann tensor, which is z bar I, z bar j. This is not possible in the previous f of r case because this is not contained in the Ricci scalar, but it is there in this contraction. Now it's possible to write it in terms of A, and it has 3 derivatives on A. This has to be canceled because we want A to be a log, so this is effectively a 1 derivative term acting on a delta function. It is precisely canceled by the k, because k is just the derivative of the 1 derivative of the metric, so it produces an equation of motion where the 1 derivative acts on the delta function. So this is how, in this case, the extrinsic curvature comes into play. And one can just match all the singular terms to convince us that this is the way. Thank you. For log gravity, one can also show this generally. This is just the right thing to minimize. So this also completes the proof in that case. We can actually use 2 methods, the cosmic grain method and the boundary condition method. Let me just briefly go over that. Log theory is very simple in particular because the equation of motion does not have any derivatives acting on the Riemann tensor. It is completely a polynomial of the Riemann tensor contracted together. So it's completely 2 derivative. And there's therefore no delta function that has a derivative acting on it in the equation of motion. We simply match the coefficients of the delta function in the equation of motion. This is rather simple to do, and we can do that. I won't show it here. It explains why the entropy only depends on the intrinsic curvature in the lower dimension, because those terms won't produce derivatives that act meaningfully on the delta function. So derivatives that act in the d-dimensional, in the lower dimensional direction does not do anything. The only dangerous terms are derivatives of delta function in the direction that delta function is active. So, but this doesn't have that. If the entropy only depends on the intrinsic thing. Whereas if we had projected Riemann tensor or extrinsic Riemann tensor, those generally have derivatives acting in the directions orthogonal to the codimension 2 circles. So that will necessarily produce derivatives of delta functions, which are in some sense more singular than a delta function itself. There's also a boundary condition method. For 4 derivative case, for the Gauss-Bonnet theory, which was worked out in this paper recently. But this is easy generalization of that argument. You simply look at a ZZ component. Turns out it just simply works. There's a simplification in a sense, since we are minimizing something which is only intrinsic. The embedding equation is particularly simple, and it just works. So let me conclude and pose some open questions. So we propose a general formula that if we evaluate this formula on a conical defect, gives a holographic entanglement entropy in the general high derivative gravity. It has 2 pieces, the usual Watt's formula and some anomaly from the intrinsic curvature. It agrees and goes beyond the existing results. And furthermore, in these examples, including log gravity to with arbitrary many derivatives, minimizing this thing also gives the correct conical defect. So in that sense, it replaces the area term in the Tech-Andagi formula. There is an immediate question, which is, does minimizing this action always locate the correct conical defect? It would be nice to show that. I'll show that it's not true. This is something I'm still working on it. If it's not true, we would have to find some other way to find the conical defect, so that we can evaluate the same equation on that defect. So one might imagine that one should minimize something else to first get a conical defect as n goes to 1, and then use this formula. But this formula, once we found the conical defect, this formula, I argue, is always the correct formula. There are immediate generalizations to other cases I've not really considered. One is when we have derivatives acting on Riemann tensors in the Lagrangian. The other case is what Sarah mentioned, which is if you couple form fields to Riemann tensors. There are also topologically massive gravity, which are not diffeomorphism invariant, but you might imagine one can use the same trick. Can we say anything useful about one-loop corrections? I haven't thought about that at all. But in the Einstein gravity case, it seems one can do it, so maybe there's some nice thing to say. Also, it would be nice to generalize the formula, including just the Einstein gravity case, to general dependent situations, where there is a proposal by Hubini and al., where they say you simply extremize the surface instead of minimizing it using Lorentzian signature. But the method here is to be modified in a quite non-trivial way because we're using the Euclidean method, and that requires reflection point in the Lorentzian evolution so that we can analytically continue to Euclidean. And in a general time-dependent situation, there is no such point. So it'd be nice to have some other formula or maybe generalizations of this so that we can use for a general time-dependent case, which is useful because it's this is something that comes a lot of in AES-CFT calculations of quantity order or just general time-dependent sources. So yeah, thank you. That's all.
So, as you mentioned in your introduction, the entanglement entropy has all these wonderful properties like strong subadditivity and so on. And I guess for the Ryu, Takani, and Nagi, one can almost kind of understand where those are coming from, right? With this correction, do you think such properties would be obvious, or would they say something interesting about geometry, or?
I would imagine that, so in the Einstein gravity case, for example, the monoticity can be related to energy conditions in the bulk. I haven't worked this up in detail at all, but I would imagine a similar story could be pursued here.
If you found some generalized energy conditions, such things are very useful to geometry analyst people, right?
Yes.
So
yes, I agree. Yeah, that's a great
That
question.
might be really cool.
Definitely people are doing this with a large conditional derivatives. That doesn't be done. I have a quick question. Is there any universality at all in this anomaly, what you're calling this anomaly?
It's
any sign of any universal?
What I can say is regulator independent. So in that sense, it's universal. But there might be another way this, so in a slightly different perspective, it could contribute to the universal terms in the entanglement entropy. Let's, for example, take a certain dimension. Then those corrections, this is actually how the Jacobson-Myers entropy was shown to be consistent with the universal terms, but the Watt entropy is not, because they looked at the contribution from these extrinsic curvature terms to the universal terms, the log terms. So I imagine that in that sense, this could also be thought of as universal, but not all of them, because depends on what dimensions you are. Some of them could contribute to the universal terms.
in the hard erupting case, the minimum surface equation, high order equation, instead of second order equation. That means you have multiple minimum surface.
That's a great question. That might be related to the difficulty of me trying to show that minimizing this gives always the correct conical defect. In the cases I've shown, at least in the Laval case, it is two derivative.
Yes, a lot of cases.
And and f of r is manifestly two derivative. In general, yeah, I imagine the difficulty just like you said,
Oh, sure.
because the embedding equation could be higher order, and therefore one needs more boundary condition. And in particular, what they are is not clear. I agree with that. So yes, I think answering this question is indeed crucial to fully solve the question of how do we locate the conical defect.
But I guess your case is split into two cases, right? Where you can treat the higher derivative Krokes as perturbative versus taking non-perturbative, and then I guess the non-perturbative theories are always unstable, right? Typically.
Typically, but still, but you might imagine that with tuning of parameters, you could get into an algo situation. So it'd be nice.
Classically, but not quantum mechanics. I think you bored about quantum.
Okay, yes. It might be related. Yeah, okay. I think I agree with the statement, and in general, I agree with this. I think this is also related to the difficulty of finding the right conical defect.
Because you might like to argue that the perturbative ones are corresponding to physical theories that aren't stick, and then the other ones are not. So.
Yeah, one could imagine a statement like that. In that case, one should be able to perturbatively at least minimize something to find a conical defect.
Any other questions?